Okay, chemistry, this is a recap video of the quiz that was given on Monday, May the 8th. You'll see a lot of these questions on the midterm, and it's a chance to redo this quiz on the midterm. And I'll go into more detail on that in class, okay? So let's go ahead and go through these quickly. Which of the following are soluble in water? So what you need to do is you had a copy of the solubility rules on the test. Okay, so here they are. So first one, calcium hydroxide. Hydroxide is insoluble with everything except 3 elements, and calcium is one of those, so that means it is soluble. Next is AgBr. So bromine is soluble with everything except 3 elements, and silver is one of those 3. That means it's insoluble. So this one is insoluble. So you just mark them down like that. NaNO3, sodium, is soluble with anything, so that's soluble. So is nitrate, by the way. Okay, and lithium is soluble with everything, no matter what, so that's soluble as well. So the answer is W, Y, and Z. So that would make the answer B. It was incorrectly keyed in as D. But I gave everyone credit for that, so you're covered on that. Okay. Next is name the following compounds. Okay, this one should be just done by memory, but the rules are the cation, the first element, retains its name. The second element adds IDE, so it's sodium chloride. That's table salt, so that would be C. FeO3. So iron can have more than one possible charge. But oxygen can't. Oxygen can only have a 2- charge, and you have 3 of those. So that equals 6-. And that means 6-. And that means that, okay, and number 4 I threw out. I gave everyone credit for that. So we're going to move on to the free response. Okay, formal charge, we corrected this, thanks to Jacob, so it's those are minus signs there. Okay, so first hydrogen, number of valence electrons in hydrogen is 1 minus lone pairs. So the first one is just what does it naturally have when it's not bonded to anything? It has 1 valence electron. Now you subtract the lone pairs. There are no lone pairs in hydrogen, minus half of the bonding electrons. There's 2 bonding electrons, so that equals 0. Carbon has 4 valence electrons in its natural state. There are no lone pairs in this particular configuration of carbon, and it's minus 1/2 of the bonding electrons. There are 8 of those, so it's 4 minus 0 minus 4 equals 0. And finally, nitrogen has 5 valence electrons. I should be labeling these. 5 valence electrons is natural state. You see it has 2 lone pair electrons there, not lone pairs, lone pair electrons. Minus 2, and then it's minus 1/2. And there's 6 bonding electrons there. So 5 minus 2 minus 3 equals 0, so that's the formal charge of the entire molecule. Okay, next I ask you to create a covalent structure for NCO. So the first thing you do is add up the valence electrons. So nitrogen, there's 1 of those times 5. Carbon, there's 1 of those times 4. Oxygen, there's 1 of those times 6. And then you have the negative charge on the overall molecule, not just on the oxygen, and that's going to give you an E- of 1. You add that up, 5 plus 4 plus 6 is 15, plus 1 is 16. Okay, so that's the answer to that. Show the octets around the terminal atom. So that was one of the steps in getting to the answer. Some of you, even people who knew how to do this, were confused by this. So I went ahead and just gave everybody credit for this. So, okay, so all I'm asking you to do is this. Actually, you should create single bonds between the central atom and the terminal atoms. Okay, that gives you 16 electrons. So that's a step toward getting the final answer. But it's not the final answer because carbon doesn't have an octet. So the way you do that is you take any two pairs from the outside and put them in the middle. And you'll end up with this. So now we have 16 electrons and everybody has an octet. You can count nitrogen, carbon has an octet, oxygen has an octet. All right, form the complete ionic equation. So what you got to remember, this is lead nitrate. It's aqueous, means it's going to dissolve in water because nitrate dissolves with everything. So if you were to draw that as a particulate diagram, you'd have a PB and then you'd have two NO3s. Now those are covalently bonded. They're not going to dissolve in water. In other words, the bonds between the nitrogen and oxygen are not going to break. Okay, by the way, the PB is a plus charge. It's a +2, the NO3 is a minus, and then you have a second one. So you have two of them. It's not going to be an NO3 molecule stuck together. It's going to no longer be together, so another NO3 minus. Okay, so the way this is going to look is PB, you've got to state that it's aqueous, and it's a 2- charge, plus, and there's two NO3s right there, two of them. Okay, and each one is a -1 charge. So there that is. The lithium breaks up, and I should put aqueous too. If you didn't do that or you left a couple of them off, I didn't hit you for that, unless you didn't put any of the states of matter on there. So it's 2 lithium. Those are each 1 plus 2 Br, and those are each 1 minus. And those are aqueous. Okay. Now we have 2 lithium and 2 nitrates, so it's going to be 2. Again, you just put the charge on each nitrate because it's 2 times that, and the charge on the lithium because it's 2 times that. And then finally you have your precipitate or your solid. You don't have to put charges on that. You should put the state of matter. So it's PbBr2. That will not dissolve in water, and that is a solid. So that's the complete ionic equation. You do not need to do the net ionic equation. All right, come on down here. So you just have to do one of the calculations and then multiply it by 2. So you have a carbon-carbon double bond. Okay, and there you have a carbon-carbon double bond. And so you come over here and carbon-carbon double bond is 620 right there. Okay, so you have one of those, and now you have 1, 2, 3, 4 carbon hydrogen single bonds. That's right there. It's 414. So it's 4 times 414. So this is going to equal 620. This is going to equal 1,656. Now you can add those two together, and you get 2,276. Now you have 2 of these molecules, so you multiply that by 2. I don't care how you did it. If you calculated it twice, I don't really care. As long as you get the show the work here and get the right number. And what that's then going to give you is 4,552. You should put kilojoules per mole, but if you didn't, that's okay. Okay, so that's your answer for that. Okay, now we have a Hess's law problem. Okay, so in these types of problems, I'd like to rewrite the equations down below as I change them. So equation 1a, so this one's going to, in other words, come down and be there. Okay, so what you should do is go to the target and find something in the target that only appears once down here, okay? So let's try N2O. N2O only appears in equation 3. So we're going to start with that. That's a good one to start with. So we look at it and we see in the target it's 1 mole. You got to compare 2 things. How many moles, what's the coefficient in other words, and which side of the arrow does it end up on. So here's the only N2O down here. It's on the left side of the arrow, and that's where it should be because that's what the target says. But you have 2 moles. You only want 1 mole. So what this is going to be is a times 1/2. So I'm going to rewrite this equation. I'm not going to reverse it. I'm just going to rewrite this. And so it's going to be 1/2 of this is just going to be N2O. So now this matches what's in the target. That's what we want. And then you're going to have this. 2N2, but you multiply that by 1/2, so you get N2, plus O2, you multiply that by 1/2. It's one of the rare times in chemistry where you have fractions as coefficients. Okay, and then you got to multiply this by 1/2, so the delta H is 1/2 of 163, and that's negative 81.6, and it's kilojoules. Okay, so we've taken care of that. So I like to put a line through this and just be sure I know that I've used it, okay? Now what else do we have up here? We have NO2. There it is right there, and it's nowhere else. So NO2 is on the right side of the arrow here, but it's on the left side in the target, so we need to reverse this. In addition, it has a coefficient of 2, whereas the coefficient in the target is 1. So what we need to do is reverse equation 2 and then multiply by 1/2. So I'm going to do those both in the same step here. So this is going to come over. It's going to become NO2. So we turned it around, put it over there on the left side of the arrow. So now it matches up with the target. That's what we want. Then these two we have to put over on the other side. So half of NO is going to be NO plus half of O2. That's going to flip over to the right, and that's going to be half of O2. Okay, so now what we need to do to this number is we need to make it a positive because we reverse the equation. You reverse it, you change the sign, so it's positive, and then we multiply it by -2. Okay, so that gives us delta H now. So again, the -113 becomes a positive 113, and then you divide it by 2. You multiply by 1/2. So that equals 56.55. That. Okay, and then finally equation 1. Let's see what we got here. Well, let's see. We've got 2NO here, but this is a little tricky because you got that NO down there, this NO that came here. So what else do we have? We have N2. We've taken care of that. So what we're going to do with this one is nothing. Okay. So we're going to put this as N2 plus O2 gives you 2NO. Okay. So now we cancel anything that's on opposite sides. So the N2 there cancels with the N2 on the left side there. The NO2, there's no other NO2s here. So it's on the left side, so we're going to put it down here. Go ahead and draw the arrow. It's on the left side. I'm going to put a box showing that I used it. We got N2O here. It doesn't appear anywhere else, so I'm going to put that down here. Okay, so I'm going to put a box around that saying that I used it. All right. And we have an O2 on the left side here, and 1/2 O2 plus 1/2 O2. They're on the same side, so you add them. So 1/2 plus 1/2 is 1 O2 on the right side of the arrows. Here's your arrows. And 1 O2 on the left side of this arrow. So you add that up, it nets out to 0. Okay, 1 minus 1/2 minus 1/2 is 0, so the oxygen is gone. So we can cancel those out. And finally, here we have, this was the tricky part, we have a 2NO and an NO. They add together to make the 3NO that we have up here. So the equation, we've been able to replicate this target equation with these equations down here. Okay, oh, and the one thing I didn't do up here is it's 180, and I didn't change equation 1. So delta H equals 180.7. So now you add all these up, and you get 155. Just add these up. 0.65 kilojoules. Okay, and that's your answer. That's what this is. Okay, that's the unknown enthalpy that you recreated. Okay, it's a little bit of a challenging problem, but we did this exact problem in class on the assignments. Okay, And by the way, I should write the answer there. That's where I put the spot, but I didn't mark you off if you didn't do that. Okay, enthalpy of reaction. So you're doing the same thing. You're finding the enthalpy of the reaction based on enthalpies of formation here. And it's all of the enthalpies of the products multiplied by any coefficients they have minus the enthalpy of the reactant. So it's only a little tricky in that these guys go on the left and these guys go over on the right. So let's go ahead and start doing that. So I like to use square brackets. You didn't have to. And CO2. So here we have CO2 is right here. It's negative 395.5. Put that in parentheses. You don't have to, but I like to. Plus, you're adding now 2H2O. So it's going to be 2 times negative 285.8. And now square bracket. Now what you're going to do is subtract, because that's a negative sign there, everything that's on the reactant side. So CH4 is right there, so it's negative 74.8 plus oxygen, but oxygen is 0, so you can go ahead and write it there. All right, so when we add these two numbers up right here, we get negative this plus 2 times this, negative 965.1 minus, and it's negative 74.8, so minus a negative is a plus, so you can write that as, I'll just go ahead and write it as a minus a negative, and the 0 goes away, so this basically becomes a plus, so that gets you negative 890.3 kilojoules. Okay, and that's your final answer for that. Okay, finally, this is a calorimetry problem, just like the one you did in class. Okay, so the formula is Q equals MC delta T. All right, so the mass. You want to know the heat entering the surroundings. So the surroundings is the sodium hydroxide and the water together. So the way you're going to write that is Q of surroundings equals 500 grams of water plus 10 grams of sodium hydroxide. You use the specific heat of water because you don't know what it is, and it's pretty close to that anyway. I'm not even doing units of measure here because it's the formula shows. And if you didn't, of course I didn't mark you off for it. And the temperature went up by 14.3 degrees. And so you get the Q for the surroundings. This is heat coming in. And so that is going to equal, and that's going to equal 30,485 joules. Okay, positive because it's entering the surroundings. So what is the heat exiting the chemical bonds? You didn't have to write this if you just went ahead and did it. But Q, negative Q of system, that's the chemical bonds, that's what we're studying, equals positive Q of the surroundings. Okay, so it's simply going to be negative 30,485 joules that came out of the reaction. Okay, the last step was what's the molar heat of the solution, of the dissolution of this. Okay, so you have this, negative 30,485. And where did that heat come from? It came only from the NaOH, and there's 10 grams of that. So not 510. That's the solution. That's how much went into the solution. So you use the mass of the total solution. But now we want to know heat coming out of the system. So that's 10 grams right there. You multiply that by molar mass because you want to find out how much heat in joules, I should put, per mole. So therefore we have 40 grams of NaOH over 1 mole of NaOH. Okay, over 1 mole. So grams cancels. So you have 30 times 40 divided by 10. 40 divided by 10 is 4. So that's going to give you 121 940. If you put a negative, that's okay, but you just express it as just a positive number. That's the heat of dissolution. Joules per mole. That's what you want to know, the heat per mole. All right, if you change that to 121.94 kilojoules, that's fine, but you didn't have to do that, okay? All right, so that takes care of this. You're going to see a lot of these same problems on the midterm on Friday, May the 12th. So be prepared for these, okay? All right.